Hey, good to see you again. I'm Mani Kanuja. Last time I promised you the bytes that are really filling your GPU up, and I said it isn't your weights. So let's start with the weights anyway, because they're the easy half. An 8 billion parameter model in 16-bit comes to about 16 gigabytes, and we worked that out a couple of episodes back. And what does that 16 do when your traffic changes? Nothing. One user or 1,000 users, a short prompt or an enormous one, it is 16 gigabytes and it just sits there. So put that model on an H100. 80 gigabytes of memory on the card, 16 of them gone, 64 left, right? So how many people can you serve on what's left? Hold that question because it's the one I want to answer properly today. And the answer isn't a setting you pick somewhere. It's a division you can do yourself in about a minute. And what's going to fill up that 64? Your KV cache. We met it back when we looked at prefill and decode, and one line brings it back. As your model reads your prompt, every layer works out two things for every token, called keys and values, and it stores them so it never has to work them out again. And does that store sit still the way your weights do? It doesn't. It grows with how long the conversation runs, and it grows with how many people are talking to you at once. So your weights are a constant, and your cache is a variable. And today we put a real size on the variable. So, what's actually in there? Let's build it up one piece at a time because I want you doing this on your own model tonight rather than trusting my arithmetic. Take one token sitting in one layer. What gets stored for it? Now, your model doesn't do attention once per layer, it does it several times side by side, and each of those parallel copies is called a head. And every head keeps its own keys and its own values. And a key is just a short list of numbers, and so is a value. So, what do you multiply together? 2, because you store a key and you store a value. Then the number of layers in your model, and then the number of key and value heads. Then how many numbers wide each head is, and how many bytes each number costs you. And then at the very end, how many tokens you're holding. Let's do it for real on Llama 3's 8 billion model. And every one of these is sitting in the file that ships with it. 32 layers, 8 key and value heads. Each head is 128 numbers wide and it's 16-bit. So that's 2 bytes a number. So 2 times 32 times 8 times 128 times 2. And what does that come out at? 131,000 bytes. Call it 128 kilobytes for one token. Now, one of those numbers will catch you out, and it's the 8. Why that one? Because 8 is the number of key and value heads, and that same model has 32 attention heads in it. So if you grab the 32, you'll be 4 times wrong before you've even started, right? Modern models deliberately keep far fewer key and value heads than attention heads. And why they do that is a whole module later in this course. Today, you just need the right one off the page. So go and open the config file for the model you're actually serving. On Hugging Face, it's called config.json, and it's right there on the model page. You're looking for the number of hidden layers, the number of key value heads, and the head dimension. And if there's no head dimension listed, take the hidden size and divide it by the number of attention heads. Multiply those the way we just did and write the answer down because everything else today is that one number multiplied by something. And of the 6 numbers we just multiplied, how many do you actually control? 1. The bytes per number is the only one you get to change after a model is trained, and there's work later in the course on doing exactly that. So a token costs you 128 kilobytes on the small model. And what does it cost on the bigger ones, the ones you'd reach for when the work gets hard? Same arithmetic, different config file. Llama 3's 70 billion model has 80 layers instead of 32, and the same 8 key and value heads and the same width. So a token there is 320 kilobytes. And the 405 billion model has 126 layers and still 8 key and value heads. So a token is 504 kilobytes. Now look at what just happened because this surprised me the first time. The model got about 50 times bigger and the cost per token went up by about 4. So is your KV cache really tracking the size of your model? It isn't. It's tracking the shape of it, and mostly it's tracking how many layers deep it is and how much does that shape matter. That 70 billion model has 64 attention heads and 8 key and value heads. So what if it had 64 key and value heads, one for every attention head? That's how attention was originally built, and plenty of models still work that way. Put 64 into the formula instead of 8, and a token costs you 2.5 megabytes, 8 times more on the same model with the same weights from one number in the config, right? And one full length conversation on that version would want about 340 gigabytes of memory all to itself. That's more than 4 H100s hold. And you don't have to take my word for the arithmetic either. DeepSeek published this same per token comparison in one of their own papers, and their figures and the ones we just derived are the same numbers. They list 516,096 bytes a token for the 405 billion model, and that is our 504 kilobytes, because a kilobyte here is 1024 bytes. And their own model, far bigger than any of the ones we've done, comes in at about 70,000 bytes a token, less than the 8 billion model we started with. So how do they do that? A different design for attention. And that's a whole module later in this course, and it's one of my favorite parts of it. So what do you take from all that? When you're weighing up two models, don't stop at the parameter count. Go and put their layer counts side by side and their key and value head counts, because those two are what your memory bill is actually made of. So now let's take that 128 kilobytes somewhere uncomfortable. That 8 billion model advertises 128,000 tokens of context, so somebody can genuinely paste a small book into it. And what does one of those conversations cost you? 128 kilobytes a token times 128,000 tokens, and that's about 17 gigabytes. And what did the entire model weigh? 16. So one person, one conversation, and their cache is bigger than your whole model. Not a slice of it, bigger. And who gets the benefit of your weights? Everybody on that card. And who gets the benefit of those 17 gigabytes? Exactly one of them. And there are models advertising 1 million token windows now. So keep this same shape and run it out to 1 million tokens, and one conversation asks you for about 130 gigabytes, which doesn't fit on the card at all, weights or no weights. So when somebody asks you to raise the context length you support, hear that properly. They're not asking for a config change, they're asking you for memory, and you should go and price it before you say yes. So why does this thing behave so differently from your weights? 3 properties, and once you've got them, most of what happens to a busy server stops being surprising. And the first one we've already watched. It grows. Your weights are that same 16 gigabytes no matter what your traffic does, and your cache goes up with every token and every user. So it grows with all the things you'd actually like to grow. The second one is the one people miss, and it's about sharing. Remember the van we sent out to the warehouse a few episodes ago? Your weights get pulled out of memory once, and every request that happens to be waiting rides along on that same load. And that's why batching works at all, right? So does your cache work like that too? It doesn't. My keys and values are mine and yours are yours, and there's nothing in mine that helps you. So 10 users means 10 separate caches sitting side by side. There's one exception worth knowing about. If 2 requests genuinely start with the very same text, say a long system prompt at the front of everything you send, then the front of that cache can be reused, and there's a technique for that later in the course. But when you're sizing a machine, assume no sharing. That's the honest default. And what's the third one? Your model doesn't just store that cache, it reads it, all of it, on every single step. So writing one word means dragging your weights out of memory and dragging the whole cache out along with them. And we said last time that this stage is memory bound, and it does about one operation for every byte it moves. So a byte of cache isn't only room you gave away, it's time you pay again on every token for the rest of that conversation. So let's go back and answer the question we started with. One H100, one 8 billion model, and how many people can you serve? 80 gigabytes on the card, and 16 of them go to weights. And do you get the other 64? Not quite, because your server needs working room while it's computing, so call it 60 and be a little conservative. So 60 gigabytes divided by 128 kilobytes a token, and that's about 450,000 tokens. That's your budget, not each. That's everybody on the card added together. So, what does that actually buy you? If your users are having short conversations, say 8,000 tokens each, you can hold somewhere around 50 of them at once. And if they're using the full 128,000 that you advertised, you can hold three. Three. Same card, same model, same code, and nothing wrong with any of it. So go and do that division for your own setup tonight. Your GPU memory minus your weights minus a bit of working room divided by the per token cost you worked out earlier. And then put that next to the context length you advertise and the number of users you promise somebody, and see whether those two things can both be true at the same time. Quite often they can't. And it is so much better to find that out on a piece of paper than in production. So, where does that leave you? We started by loading a model onto a card and watching 16 gigabytes disappear, and that felt like the expensive part. It wasn't. That 16 is the one number on that card that is never going to change again. And everything after it is cache, and cache arrives with every user and every word they send you. So, what would I do tonight? Both bits of arithmetic, and neither of them takes long. Get your cost per token out of your config file and get your token budget out of your GPU. And between them, they tell you how many people fit. And next time we look at whether the hardware you're paying for is actually being used. Because your card can be completely full and completely busy and still be delivering a fraction of what you bought. And the way you measure that is different for each of your two stages. See you next time.